Hello everyone, my name is Charlie Scott from the University of Strathclyde, Advanced Forming Research Centre and the Future Electrical Machines Manufacturing Hub, and today I'm going to be talking to you about my PhD topic, which is the lightweight design and manufacture of electrical machines. My background is in design and manufacture, and the goal of my PhD is to optimise the manufacture of electrical machine components through various lightweighting techniques and the design of multifunctional components. In my PhD, I've mainly finished with the literature review section of the project, and I'm now exploring the next stage in my research process. The motors that my PhD will focus on are the high-performance, high-integrity permanent magnet synchronous motors that are targeted towards automotive and aerospace. In my research so far, I have explored a variety of topics and potential different directions to take my research. These topics include general research into electrical machines, soft magnetic composites, additive manufacture, topology optimization, composites, and system cooling. As part of my research so far, I've been lucky enough to pay a visit to Waste Electrical and Electronic Equipment Recycling Scotland's facilities to find out more about motors in real-world applications. And they were also kind enough to provide us with some electric motors which we could use for teardown exercises and further research. The applications of these motors ranged from coffee machine bean grinding motors and water pumps, all the way up to industrial machine motors. The biggest takeaway we got from this activity was the realization that these motors were not designed to be easily taken apart, with all motors making use of interference fits between components. This made disassembly very difficult and would mean a lot of the time these motors would not be economical to repair. This is an issue that could potentially be rectified throughout this project. A major factor of motor performance became apparent to me early in the project, and that is motor cooling. Some novel cooling concepts I've come across in my project so far include the addition of a back iron extension which claims to help reduce peak winding temperatures by up to 26%, integrated stator and rotor liquid cooling, and a mini heat exchanger that fits directly in between the windings in a direct wind machine. I have also explored the stated performance figures of currently available high-performance motors to find out the sort of performance that is expected from modern machines. Electrical machine components can be divided into two main categories: those that are magnetically active and those that are non-magnetically active. The non-active components are the case, rotor shaft and rotor hub. The active components are the stator and rotor cores, stator windings, and the magnets. The active components are what give the motor its performance characteristics, while the non-active components, despite still being important, are seen as less critical to motor performance, particularly power to weight and torque to weight. Typically, the mass of non-active components is roughly equal to the mass of the active components. This became particularly apparent in a paper produced by Rolls-Royce and the University of Sheffield that described the design, construction and testing of an engine starter generator for more electric aircraft. Despite effort being made to reduce the mass of the non-active components, only 53% of the overall weight is contributed by the active components. In an ideal motor, the mass of the non-active components would be minimized as much as possible. For this reason, my PhD is currently mainly focused on these non-active components. It is important to keep in mind, though, that some of the non-magnetically active components do have influence over the performance of the motor. For example, the maximum performance of a motor is heavily dictated by its cooling capacity, which is predominantly afforded by the casing design. In general, there are two main methods for cooling motors: air cooling and liquid cooling. A typical air-cooled machine looks something like this. It usually has a cast aluminium casing with fins on the outer surface to increase surface area. Often, a fan will be mounted on the rear of the machine to stir up the surrounding air. This type of system is usually very robust, with few parts to go wrong. However, it lacks the outright cooling capabilities for high-performance applications. Very little work has gone into the refinement and optimization of this type of motor design, and as such, these motors have remained very similar for decades. For high performance applications, liquid cooling is the primary choice. Liquid cooling traditionally has a higher capacity for heat dissipation, but does come with drawbacks such as high overall system weight and increased complexity. So all this got me thinking, could you optimize air cooling enough to compete with liquid cooling whilst not having the associated downfalls? One of the first things that became apparent when comparing air and liquid cooling is that the total surface area available for heat transfer in a liquid-cooled system is far greater than on an air-cooled motor case. This is something I've started exploring. Up on screen is my very early concept for an air-cooled motor case with increased surface area. This concept utilizes a honeycomb structure around the outer circumference, which aims to vastly increase the surface area, like the fins found in radiators. A centrifugal fan is used to suck air in through the back of the motor, which will flow through the outer channels through the honeycomb, where it will be exhausted out of the case. A second big consideration for effective air cooling of high-performance machines is that the whole system would need to be designed to allow for sufficient airflow around the motor. Generally speaking, electric vehicles have their motors located centrally with limited access to fresh airflow. Because of this, it's looking like the whole system will need to be integrated and designed from the ground up to accommodate the chosen cooling method if an optimal solution is to be found. Moving forward with this concept, I've been doing some structural analysis on the casing, both theoretically and through simulation, to discover how the forces act within the motor case. Following on from this, I started with the thermal analysis for my design, and I have spent time developing my CFD skills in order to aid this. But at this point in my research, I did a bit of self-reflection, and I realized that I had strayed too far away from the initial project goal with this concept, and I didn't have a concrete reason for pursuing this honeycomb concept. With that in mind, I've recently taken a step back to focus on the topic of lightweighting on the non-magnetically active components for the motor. For this, I've decided to focus on designing a lightweight case for a hollow coiled concept motor that is being developed by fellow FEMM Hub members at the University of Sheffield. By basing the case around this motor concept, there is less of a thermal requirement on the case, so there is more scope for freedom in terms of lightweighting. Some initial ideas that come to mind include removing unnecessary material, similar to what has been done with the Siemens SP250D, or incorporating other lightweight materials such as magnesium or carbon fiber reinforced composites that would traditionally not be usable due to their lower thermal conductivities. I do hope to continue my work on the high-performance air-cooled motor case at a later date. Looking into the future, one of the things I would like to investigate is the use of additive manufacturing, as there are features which can be incorporated into designs with additive manufacturing that are simply not possible with traditional manufacturing methods. The plan would be for a comparative study to be conducted where two cases are developed, one that utilizes all the features only possible with additive manufacturing, and one with optimizations for traditional manufacturing. Up on the screen is an example of the types of features that can be implemented with additive manufacturing that would not be possible traditionally. This example is a heat exchanger produced by the company Hayata. Additive manufacture also opens avenues into other technologies, such as topology optimization, which would allow for further lightweighting options. The goal of this study would be to determine if there is potential for even more performance to be unlocked in electric machines using these methods. This is all I've got time for, so thank you for listening, and if you have any questions, feel free to contact me on my email. Thank you.